Yeah, the issue is to discuss the density matrix for the P-NAV system. This is the general expression based on the hermiticity. The fact that this trace 1 fixes this coefficient, right? And then we are discussing what are the properties of this vector B for this thing to describe a density matrix. First, we observe that for B of length half, or B square length 1/4, we get a projector. So the square of it is equal to itself. And so this is a projector in the sense that it projects any vector in this two-component vector space onto eigenstates of this, right? Of this operator. This would be the pure case, right? If we relax this condition that B square is equal to 1/4, we can relax it only in one direction. This must be less than 1/4 because otherwise it will have negative eigenvalues, right? And that's all. So this is condition. Strictly less is a condition for having a density matrix, which is not a pure state, but this can be used also in the relativistic case. This reason I'm discussing it. Okay. And what are these B? We can express the B in terms of expectation values of the spin operator. No? Our spin operator is what? S is h bar over 2, right? Times sigma. No? This is the spin operator. H bar because it has the dimension of an action. 1/2 because the spin 1/2. So the eigenvalues of this are h half minus h half. These are the two values of the spin, say, for example, for the electron. So we can relate these B's here, there are 3 numbers here, right, to the expectation values of S. No? What are the expectation values S? Well, we have to compute them using rho, right? Expectation value of S is by definition trace rho S, right? Okay. Now, when we do this, the identity here does not contribute. This one does not contribute because the sigmas are traceless, so only this contributes, right? So this is trace 1/2, no, because there is a 1/2. No, there is no 1/2. There is the B dot sigma, and then we have S, which is, so this is h bar over 2, and then there are the sigmas here. So this is summed over, right? Now trace sigma I, sigma j is 2 times delta j, right? So then this you get h bar over 2, another 2 coming from here, so 2bi, right? Okay, I denoted si. Let me put si here, and this is sigma I, right? So this is what it is. So h bar bi. So we learn that these coefficients are essentially proportional to the expectation value of the spin. So a better way of writing this density matrix would be rho is 1/2 identity plus B we said is S over h bar, so 1 over h bar here, and here we can write in this way, S dot sigma. Okay. So this is the expression for the density matrix. So the part coming with the sigmas is related to the expectation values of the spin, and we observe already in the example of the half 1/1 that if this is not there, in fact, right, only this is there, the expectation value of the spins are all 3 are 0, right? So this is completely unpolarized, situation. Right? We can have that in the mixed case. Can have S equal to 0, all the three components, so in which case rho is just 1/2 the identity, right? This is already solved. This is a possibility, and this cannot be true for a pure state, which is clear from what we are saying, right? In the pure state case, n cannot be 0. This n, right? But you were also, one can check this by simply computing the expectation value of the spin, consider an arbitrary state, alpha beta, take the matrix element of that state in the state alpha, I mean, this bra and ket, and verify that if you impose that all the S are 0, then you get that the state is 0, essentially, so that it is not a state. So this is the yeah, this is what I wanted to say. By the way, I will add some notes on this topic here, density matrix that we were discussing in the last couple of lectures, so I will distribute. So maybe the last thing I want to discuss, another example of quantum mechanical system, which is
the block sphere.
Sorry?
You could discuss the block sphere, how does the block sphere, that you have a shell with pure states and inside the mixed states.
Maybe you can
tell
us what it is.
Block sphere.
The
block sphere.
Yeah, but you can you discuss it at the blackboard?
I don't know. I'm okay.
So the block sphere is what? I know that you can construct density by averaging over the S2, the two sphere. I don't know what you have in mind. I know there is such a thing, but at this stage I'm not ready to discuss it. Yeah.
Just mentioning.
Yeah, okay. No, the last thing I wanted to discuss is, as I said, an application to an interesting quantum mechanical system, which is the case where you have a charged particle in a magnetic field constant magnetic field, so some H. Now, this particle can have spin or not. Okay, let's forget the spin does not add anything particularly complicated to it. Okay, so what is the, so we have a particle, well, yeah, we have a particle in a constant magnetic field. For simplicity, you can imagine it to be along the Z axis, right? And so we have a charged particle, charge Q and mass M, say, in this magnetic field. And first of all, there is a classical story and a quantum story, right? What is the classical story? Remember, what is the motion of this? Is some helix, right? So if this is oriented along the z-axis, it moves with constant velocity along the z-axis, but say it does like that, right? Around some center here, say x0, y0, no? And it moves up, some helix. Up or down, that depends on the sign of the charge. Now, let me just mention what is the classical, how you discuss the classical. The point is that this motion is due to the Lorentz force, which is always the cross product between the velocity and the magnetic field, right? So if you have something oriented in that direction, the force will act on the xy plane, no? It will be trivial in the direction of the magnetic field. So what is the classical Lagrangian is 1/2 m x dot square, right? And then you have the interaction with the magnetic field, or in general could be also some electric field. There is some charge here, and there is the scalar potential phi, and then minus, say, x, what is it? X dot A. Right? This is what it is. This is the, say, A0, and this is the vector potential AI, right? And this is the way. So this gives electric field interaction of this particle, and this is the magnetic field, and then from this you can derive the equation of motion, right? By the usual procedure, right? P dt dl over dx dot, right, is dl dx, no? So this gives contribution from this term and from this term also, right? This. And this is coming from this and also that. Right? Putting everything together, you find what you find. You find that the force, so m x dot, x double dot, right, is a force, and that is Q, and then there is the electric field, which is, let me put E, plus x dot, no, better to write it, yeah, H. Right, this is what you get. No? These terms come from this part, right? This is A0 gives the electric field, right? So you have F0i and Fij, right? This is D0 AI minus DI0. This is essentially the electric field, and this is DI AJ minus DJ AI, and if you contract with an epsilon, you get H, HI, right? So this is the equation of motion that you get from this Lagrangian. By the way, this will be there. This type of Lagrangian will be also there in the relativistic case. This is always there. This is the same form that you have in the relativistic case. In the relativistic case, of course, this is not the correct expression for the massive particle. It will be the square root of something which, once you expand the small velocities, you get this, right? The non-relativistic limit. So this is the Lagrangian. From the Lagrangian you can derive the Hamiltonian in the usual way. First derive the momenta, right? The P is dl over dx dot, right? And apply the usual rule, P x dot, right, minus L, expressed everything in terms of the momenta, and you find the Hamiltonian. Right? The Hamiltonian is, once you do that, 1 over 2m, and then there is P momentum minus Q A. I don't include the velocity of light. This usually there is a velocity of light here divided here over c. Let me put it here. Q over c A square, right? And then there is the contribution of say Q phi, the scalar potential, the AZ. No? So we are interested. Let's forget about that. We are interested in this thing. Now you see, what is x dot? Well, x dot is just this thing here, right? 1 over m p minus q over c over a dot over a. So this is the velocity, right? Now the commutation relation. Now let's go to the quantum case. The commutation relation between among the p's, of course, are the 4 pi pj's in delta I is 0, right? And then p xi pj is I h bar delta ij. These are the usual commutation relation. Okay. But you see that the velocities the velocities on two different directions don't commute, right? In general, because of this term, right? Because if you do vi vj, this is sum of 1 over m square, and then you have pi pj commute, ai aj commute. Okay, but there is a problem with the cross terms, right? The p with the a's, right? The a's are functions of x's, right? And these are derivatives with respect to x's, right? pi is I h bar d dxi, right? So clearly, when you do this commutator here, this acts here, no? So as a result, you get something that you can fix the coefficients here, which is proportional to fij, right? Because it's the derivative with respect to I of aj minus the derivative with respect to j of ai. This is just fij, no? So if there is a flux, non-trivial flux, the velocities don't commute. The velocities along different direction don't commute. Okay. This is because we impose that the momenta commute actually, right? So you cannot have both, right? But since the momenta must be canonical, must obey canonical commutation relation, that we fix to be like that. And the consequence is that these are in general non-zero. If the Fij is not 0, this is not 0. Okay, so this is the one perhaps surprising thing, but this is what it is. Now, suppose you go back to this problem of discussing what happens quantum mechanically if you have a particle of charge q mass m in this constant magnetic field along the z-axis. Now, we know what is the magnetic field. We fix it to be, say, H is 0, 0, H, and something like that, no? the third component. But in the Hamiltonian, this is the Hamiltonian, right? We take this to be also the quantum Hamiltonian, right? The only point is that these are operators in general. Yeah, so now, you know, here, what appears here is not the magnetic field, but is the vector potential. Now here comes, of course, ambiguity, freedom that what you have in this problem, because there are many choices of the vector potential which give rise to the same magnetic field, right? There is the issue of gauge freedom, right? This is gauge invariant, right? In the sense that if you change AI going to AI plus a derivative of any arbitrary function capital lambda, this remains the same, right? So I can use this freedom to choose a convenient vector potential. This is is a typical problem that you will have when you work with vector potential. Choose a gauge. This is a problem, choosing a gauge, that you will see in quantum field theory how the problem will be addressed. Okay. Clearly, if you do that, nothing changes here, right? Because the two terms cancel, right? So we can choose for our convenience. For example, you want to get this. You can choose, for example, AX to be minus HY and AY and AZ equal to 0. Because what is the HZ is dx AY minus dy AX, right? This is 0. And so this reproduces just H. No? So Hz, the component of H along direction Z, is given by some H, some constant magnetic field. Of course, here we are assuming that this is constant. So then the vector potential is linear in the coordinate. No? So this is Hamiltonian. By the way, if instead of having just particle with charge and spin 0, say, you had the charge a particle with some spin, there will be an intrinsic magnetic moment which will interact with the magnetic field, right? So the Hamiltonian will be this plus a term which takes into account this interaction. What is the term? Is the essentially up to constant the spin dotted with the magnetic field, right? And say if you have a spin half system, in this case will become, no, in this case suppose you add here, just to mention that this does not introduce any complication. If you add a term which is mu magnetic moment dot H, this is the form of the interaction, right? This mu is so H is just Hz, right? And this will be, so the mu's are proportional to the spin, no? So the sigma Pauli matrices. So this will be something like, if you put together all the constants, which enter here, you will have some constant here times sigma 3, right? No? Some dimension for constants here, times sigma 3. Sigma 3 is plus 1 or minus 1 eigenvalue. So this will simply add or subtract some quantity to the spectrum of this Hamiltonian. So once you, the hard problem is to diagonalize this Hamiltonian. Once you have done this, then this will not introduce any complication. Okay? So this is the problem that, so this problem was solved by Landau in the 30s of the other century. And so we have to substitute here this. So the only, the non-trivial part is the one involving the x here, right? Okay, so there is what? This is A, so you have 1 over 2m, and this is px minus q over c ax square plus 1 over 2m py minus q over c ay square plus the third direction. So this AZ is 0, we said, right? And let's see, maybe I wanted to have a different, no, this is okay, yeah, this is okay. So AX is what? Minus HAY, so here we put, this is HY, right? This is what it is, no? AY 0, so this is, we can remove that, right? This is 0, so this becomes this. Okay? Now, first of all, let's look at these various terms, right? This is the Hamiltonian. What can we diagonalize? What quantum numbers can be diagonalized, meaning that commute with the Hamiltonian? For sure, PZ, right? Nothing, there is no Z appearing here, right? This. And not Py, right? Because Py is conjugated to Y, so this is a non-trivial part, right? This part and this part. But Px, yes, right? There is no x here, right? So Px can be taken to be diagonal number, quantum number, right? So we can try to find eigenfunctions of the form plane waves in Px and Pz, no? E to the I Px x over h bar, e to the I Pz z over h bar, right? And then we'll have the non-trivial part, which will be some function chi of y. This is non-trivial. These are plane waves, no?
Why did we choose the wave plane solution?
Because this is this is, suppose you have just this term here. This is a free particle, right? The free particle, eigenstates of the free particle are plane waves, right? And the same for the x, right? We can, so we take P to be diagonal, right? And then you can plug this here. So now this, we can consider this to be just a number, right? That's a number, no? The wave number or the momentum in along that. No? This is something which stays by itself. It's some contribution to the total energy, which is the usual contribution of a plane wave, p squared over 2m. And p can be anything, right? Any continuum momentum, right? So the non-trivial part, is this one. No? But now you see 6px is just a number. This is very, if you look at this is what? What is this Hamiltonian? This is second derivative with respect to y, right? Minus h squared over 2m d, no, this is this. This is harmonic oscillator, right? Yeah, precisely. So you have minus h square over 2m. This is this, right? And then this, I can rewrite it, right? In the form y minus some constant, which I call y0. No? I can write this as, I want to write it as 1/2. This is the way the harmonic oscillator Hamiltonian appears. Omega square, some omega s square, right? The y square, right? This would be the standard canonical harmonic oscillator. Okay. Now, what is the difference of that with respect to that? Well, we can, of course, always find this form outside, right? By defining what omega is, right? Coming from these numbers here. And why not will be given by some px times some constants here, right? So if you add this instead of suppose we add this harmonic oscillator, there would be no difference, right? If you want to find the eigenvalues, it will be the same as the usual one, right? It's simply an harmonic oscillator that instead of being near the origin, at the origin, it is translated by, say, this is y naught, will be around that, this is 0, right? But the spectrum is the same, of course, right? Y naught does not, you can simply change variables, say y minus y naught to be y prime, d over dy is also d over dy prime, and it will be the wave functions, of course, will be now peaked around y naught, not 0, but apart from that. Now, to rewrite it this way, we have to massage a little bit this expression, right? So you have 1 over 2m px plus qh over cy. If you want to write it in this form, better y come with coefficient 1 like that, right? So we can take this outside. This is square, right? So suppose we take this out. This is c over qh, and this is qh over c whole square, right? Right? I just rewrote this thing here, right? Right? And then this is, so I call y naught this thing here, c over q h px minus. No? So this becomes 1 over 2m qh over c whole square y minus y naught square, right? And this will define my, if I compare this to this expression, it tells me what omega is, right? So I have that m omega square is 1 over m q h over c whole square, right? So then omega square is this, right? So omega is 1 over m qh over c. Okay? That's all. But once you have done that, there is nothing to do anymore, right? The work, the job is done, right? Because if you are interested in the energy levels, what are the energy levels? Well, the energy levels of the harmonic oscillator, which are given by h bar omega, this omega, n plus half. So the energy levels are this omega here, n plus half, plus, remember this part here, right? This is there, right? This contributes to the total energy, but this is continuum, right? 1 over 2m pz square, right? These are the energy levels of this problem. There is an harmonic oscillator and then a plane wave.
Px.
Huh?
By the same reasoning, then we also have 1 over 2m px square, right?
No,
No?
no. Because px square I have taken care of.
Sorry, I confused.
But there is a point here. The fact that, you know, what is the point? What is the degeneracy of these energy levels?
2, maybe.
Huh?
Maybe 2 because of the PZ.
No, PZ, remember, if I give PZ, there is only one, I mean, this does not introduce any degeneracy, right? I give you PZ, this is the contribution of PZ. But there is only one state, the plane wave. The point is that this formula does not depend on what? Px. Because Px entered here, in this way, is the center of the harmonic oscillator. But this center is a continuum variable, right? Because it's one of our quantum numbers. So there is an infinite degeneracy, right? Because Px goes from minus infinity to plus infinity, right? So this implies there is an infinite degeneracy due to Px.
Why the fact that minus PC also gives the same contribution doesn't include another degeneracy?
Sorry, repeat again.
I can use minus PC and I have the same contribution.
Okay, yeah, you can say this is a double, I mean, this is a usual story about if the particle moves along that direction, on this direction is the same energy, yeah, okay. So for a given energy, if you wish, even the plane wave, for a given energy E, which is P square over 2m, you can give plus P or minus P. Okay, yeah. This is a reflection, yeah, okay.
This result doesn't depend on the gauge choice, of course. The A.
Should not, yeah, it should not, although we had chosen a particular gauge, but should not depend on the gauge choice. And why is that? Because you know, making a gauge, there is this invariance that we did not discuss so far. We just discussed the fact that the field strength is gauge invariant, the magnetic field or electric field are gauge invariant quantities. That is already there in classical mechanics, right? How this reflects, what is the additional thing here perhaps, is that at the level of wave functions, we have this Hamiltonian, right? The Hamiltonian was E minus E over 2m, and then there is, in principle, okay, like that, the A0, which is just Q. Let me put Q here, Q5, right? This is the Hamiltonian. And the Schrödinger equation is the usual, d psi dt is H psi, right? Now remember that we said all the time that a overall phase on the wave function does not do anything, right? Constant phase, we discussed that issue, the constant phase. But now you see, once you introduce these couplings here, in which the momentum is sent to the momentum minus something, and then in some sense you can also interpret this as being a modification of dt, right? You said dt going to E, let me call it E, this is E in some sense, right? The energy, no? E going to E minus Q phi, right? And then you put it on the other side. And then P going to P minus E Q, sorry, Q over C, E. Now this way of getting the dependence on the vector potential in the Schrödinger equation is called the minimal coupling. It's the way you introduce coupling of a particle to an external electromagnetic field. This is called minimal coupling. Which will be true also in the relativistic situation. But now, you know, you have the freedom that of making this. Let me put a lambda here. Let me put coefficient, the constants. This is Q over H bar, I think. Then we will verify it. Some lambda, psi. This lambda depending on the coordinates, X and T. What is the statement? The statement is that if I do this change of variable here, you know, in the ordinary Schrödinger equation, there will be a mess, right? Because the derivative will act here, right? So there will be nothing simple, no? So we cannot, in the Schrödinger equation, when we don't have these potentials, this is not a symmetry, right? The Schrödinger equation will become some mess involved in the derivative here. However, if you have these new couplings with the gauge potentials, we have the freedom of changing A and phi, right, at the same time. A going to A plus some some derivative of lambda, the same lambda. Now I have to check whether this match. Let's see if I've done the. Yeah, I think this is okay. And the same for phi. For phi, of course, you will have something involving the time derivative, right? Phi minus, I think, dt of or lambda. Probably some C, I don't know. I'm not sure about that. One has to check, but anyway, if you do this and that, then you can make sure that in the end, you know, the equation is I h bar d psi dt. Yeah, I already wrote it. Okay, is this, no? Where this is that. By doing this, and also changing the vector potential, you can make things in such a way that this equation is not strictly invariant, but it picks an overall phase. It changes by an overall phase, both sides. Okay, in which case this is a symmetry, right? Because you can remove the overall phase. I'm saying that I h bar d psi dt goes to something like e to the I q h bar lambda times I h bar d psi dt equal to e to the I q h bar lambda, and then this is h psi. If you can show that, then this overall phase is irrelevant. You can just remove it, right? The trick is, of course, you know what is the trick, right? The fact that when this p, which is a derivative, p is nothing but minus I h bar d dx, right, acts here, it brings down the derivative of lambda, right? However, if I shift also A by derivative of lambda, I can fix things in such a way that this cancels. Right? This is the trick. Probably there is this C, I'm not sure about the C here. Because if I write in this way, there should be some C also. Because P is minus I h bar d dx, right? Acting on e to the I q over h bar lambda, right? This will be I minus I1, and then this is h bar cancels. This is q d lambda, right? So this is the term that I want to cancel by shifting A with something which is again a derivative with respect to lambda, right? So if I send A to A plus presumably C times d lambda, right? This should cancel this term, right? So this is the idea. Actually, the correct thing is the following. Let me put it here. And then this is then Q over C. And then you just do this. This is precisely correct. What is this? If I put a C here.
Another C will appear when we replace in P operator. We'll have another C.
No, the P.
Yeah.
The P is just this, right? No? There is no C here.
No, but if we derive, we use the formula. We just apply the operator
Yeah.
on side, so we will get another C. So if we can
Okay, this is C here. No, this is Q over C, right? No? But then A appears also with Q over C, no? Right? A is multiplied by Q over C, so if I just shift A in this way, then I don't need the extra term here, extra coefficient, because this will cancel precisely. This will becomes with a minus sign, right? So they cancel that. No, you are convinced or not? Yeah. I mean, with the definition of P, which is given by the usual correspondence, this definition of phase transformation, which is this, and this Q over C, which is that, this is what happens, right? And here there is nothing, 1 here. And the same, I mean, you can check that something like this works for the time derivative. So the point is that, yeah, you choose a gauge, but it should be that any gauge choice gives the same physics in the end. In fact, there are various, so this is a very asymmetric choice, you know, which we have chosen AX is minus YH, right? And the other two, but there is also a more symmetric choice in which you choose different from 0 both AX and AY in such a way that, again, the magnetic field is along the direction. And I mean, you can go through this procedure and find the same. So this is the Landau. These are called Landau levels. These energy levels. Plus pz square over 1. And to fix the degeneracy, actually to find to fix this problem, this infinite degeneracy is not very nice, right? But what you have to do is to put the system in some finite volume, some finite box in the xy plane. Okay, both x and y to be finite. In that case, you can prove that you can have a finite number of states. There is degeneracy, but not infinite degeneracy. So this is the Landau level problem, which is has many applications, more in condensed matter physics, I would say. So this is the quantum version of this, what do you call it? Helix picture that you have in the classical case. So this is called the gauging variance, extended to the wave functions, right? The fact that you can redefine your wave functions by phases which are x and t dependent. And this leaves, if you change also the vector potential, this leaves the Schrödinger equations invariant.
No, they put the system in, you said they put in a system in a finite box in the xy domain. So that will induce the x momentum to be quantized because of the box. Right?
The momentum, of course. The momentum will be quantized because in the box, if you have, say, this is px, right? Px is 2 pi n over Lx, right? This will be the, if you impose periodic boundary conditions, this will be px. But then, also you want that y0, if you also say that y, the center, you remember, this y0 is a function of px. No? You want also y to be confined, y0, that fixes the, So, yeah. Because if you write px in this way, this can be arbitrarily large, right? Capital N can be, but if you say that I'm confined also in y direction, then this gives a finite number of.
So there will be an upper bound on.
Yeah. This is what one does, I think, yeah. Right, so that's it. As I said, the fact that if you have a spin, this will be, plus minus some finite shift here due to the fact that there is a mu dot sigma Kaplan, right? Plus or minus delta E. But nothing changed. I mean, the picture is the same. Yeah, usually, as you will see, when you do quantum field theory, you will use natural units, in which case many of these constants will drop, right? There is no C, no H bar, so that things are simple to read, right? So this will not be there here. This will not be there, of course. The charge will be there because this is the coupling constant, right, of the particle to the electromagnetic field. That charge will be there, but H bar and C you can set to 1.
The charge will become identical to, I think, the square root of.
Yeah, that will be a number in any case. So this is a very important principle. This minimal coupling is the way you introduce, even you will see in quantum field theory and QED, the way you introduce the coupling of some matter field, like the electron, to the electromagnetic field. Of course, in that case, here we are considering the case where this is an external electromagnetic field, right? It does not have its own dynamics, no? But strictly speaking, you should consider the coupling. This also with its own dynamics given by Maxwell's equations, right? And the two things are coupled, of course, because the motion of the particle creates also a magnetic field, and then it's a coupled system, right? Here we are neglecting this interaction. The back reaction of the charge, the motion of the charged particle on the external magnetic field. No? Okay.